Hello, everyone. Welcome to this webinar. My name is Taran Packer. I am a senior simulation support specialist at GoEngineer, and I've been working with flow simulation for the past 9 years, a little over 9 years. So I've got a lot of experience solving lots of different customers' issues with flow simulation. And so far, 14 people have joined. I assume you all are interested in the topic, which is SOLIDWORKS mixing fluids using static mixers and also powered rotors. So basically, oh, and by the way, just a quick kind of housekeeping real fast, sorry. You can put your questions either in the chat or Q&A. I'll try and keep track of those and answer those. And then at the end, we'll also just have a Q&A session if there's time. Okay, so let's get into the topic here. SOLIDWORKS mixing fluid static and powered rotors. So these are the models that we're going to go over first. Before we get into actual powered rotors, we're going to start off with an inline static mixer. We're going to see what happens when we put 100-degree water in this small hole on the top, and then 20 degrees room temperature water. That's what this stands for, room temperature hot water, inline. And then it's going to go through this static mixer and mix together before it goes out of the tube. So the benefits of a static mixer are obviously you don't have to put any power into it, but the question is does it mix as well as something that you do have to put power into? And then next we're going to look at this model where we actually rotate this bar at 50 revolutions per minute. Imagine there's a big motor on the back here rotating this thing, and the room temperature water in this specific situation is going to be coming in from the side because obviously the motor's in the back, so slightly different than the static mixer, but not by much. 100 C coming in the small hole, 20 C in the large hole on the side. And then we're going to see what it looks like with static mixer with a time with 40 seconds. The powered mixer is on for 40 seconds, and we're going to see what happens with 40 seconds with the static mixer, and then compare and contrast those. And lastly, we'll just look at a free surface rotating event where we can just see what happens when water is stationary inside of a tank and it's not coming into an inlet and going out of an outlet like in the previous examples. So let's go ahead and look at these. All right. So first off, we're going to start off with this inline mixer using steady state. So this is not time dependent. It only calculates to steady state, and it shows you what that looks like. If I come to general settings, I'll show you the setup here real quickly. I do have gravity turned on. Brown arrow right there is the direction of gravity. I only have one fluid, which is water. And my initial conditions are everything is set to room temperature. Like I showed you in the PowerPoint, I have 20 degrees water coming in this port. And this port, I have 100 degrees water coming in here. I don't have time to show you this setup from scratch, so I'm just showing you what I set up previously. And then I just have an outlet, mass flow outlet, forcing the water to go at 0.01 kilograms per second out. My main goals are I want to see what the temperature of the water is at this inlet, which is going to be around 20 C, this inlet, which is 100 C, and then mostly I want to see what the temperature is of the water as it goes out of the outlet right here. So let's go ahead and look at these results. Okay, so I'm gonna show these cut plots. And this is steady state, so I can't animate this. In the next version of this, I'm going to show you the 40-second time-dependent version where I can animate it over the 40 seconds. But as you can see, at steady state, the hot water from the inlet is mixing okay right at this beginning portion. But then once it reaches the static mixer, you can see it mixes very, very well. And it goes from 100 degrees Celsius water to around 55 or 60 degrees Celsius inside of this mixer. The lower portion doesn't mix as well as the upper portion. We can also see a flow trajectories plot. Sorry, didn't mean to press that. I wanted to hide those. I'm going to look at a flow trajectories plot. So I have this inlet and the outlet set as a pressure, and then I have the outlet set as a forced outlet, which is what I showed you previously. And that's why there is, it allows water to move out of this inlet on the top, because this is set as a pressure boundary condition. But you can see there's a vortex right here, and then once it reaches the static mixer, you can see the water moving in and around the static mixer as it moves through it, and that mixes that water going through the system. All right, so now let's see what happens when we look at the powered mixer. So I'm going to go to the powered mixer here. And again, imagine back here that there's an engine rotating this mixing bar. So the setup on this was much like the static mixer. I have gravity turned on, same direction. I also have rotation turned on in the general settings. And I set it to a type of rotation called sliding. There are two types of rotation in SOLIDWORKS Flow Simulation. There's the averaging and sliding. This global rotation is just another version of average, basically averaging. So the two types are averaging and sliding. Averaging, it just mathematically calculates how the fluid would be rotating around the object that you're rotating. Sliding, on the other hand, takes the actual mesh of the flow that you mesh in flow simulation, and inside of the rotating region, it actually rotates the actual geometry. In flow simulation, there's no moving geometry except for rotational movement, which is what you can do here with the sliding rotational option. And again, the fluids are just water. And the initial conditions, same thing, 20 degrees Celsius to start off. The differences in this example are the rotating region. Let me go ahead and show that. So what you do to set up a rotating region in flow simulation is you actually extrude in a feature, a cylindrical feature. It has to be axially symmetric. So I extruded in this circular object, and basically this object has to be over the solid geometry that you want to be rotating. So that's what I did here. I made sure that it was going over this geometry. And you can see there's a little bit of space here, and there's a little bit of space back here. So that will force everything inside of it, all the solid geometry inside of it, it will force it to rotate. And then if you install a rotating region, it's really easy to put this together. All you have to do is click on the rotating region body. This can either be a part file body or it can actually be a part inside of an assembly. I have this as a part file body. Let me show that to you real quickly. Let me come back to the SOLIDWORKS feature tree. And you can see my rotating region right here as a body. So it could either be the part file body or part file in an assembly. Either one works. And then you click on that here in the blue selection box, and you give it a speed and a direction. And the direction, you can see the arrows right there. So it's really easy to set up the rotating region. Everything else is the exact same as before. Let me show the tube again. I have 20 degrees water coming in the big hole. I have 100 degrees Celsius coming in this smaller one. And then the outlet is the same, 0.01 kilograms per second outlet. The goals are the same as well. I'm tracking the temperature on the room temperature water. I'm tracking the temperature on the hot water, and then I'm tracking the temperature on the outlet. I haven't shown you these goals yet. I'm going to show it to you, the goals all at once, to kind of compare and contrast once we get to that point. So I'm going to load these results. And this was a time-dependent analysis. So you can see I ran it for about 40 seconds, a little over 40 seconds. Let me show you how to set that up. I think I might have forgotten to show that to you. There's this check mark right here, time-dependent. That's how you turn the time dependency on in the wizard. And then if you right-click Input Data, and you go to Calculation Control Options, this is where you can put in how much time you want to calculate for. I didn't know how long it would take to get to steady state. It only took about 40 seconds, it turns out. So I just put a fairly large number that I figured it's going to reach steady state in this time frame, 120 seconds. But I did stop it after 40 seconds because it had pretty much reached steady state by that point. Here in the Solving tab, this is where you can set up your time step. So this is where you set up your full time. Solving tab is where you set up your time step. You can leave it on automatic, which is what I did, or you can change it to manual and actually put a manual time step in. You have to be careful with the time step. You have to make sure that it's small enough that you capture all the data properly, but large enough that it doesn't take forever to run. So I usually leave it on auto at first, just to see if it takes a long time. If it's taking a long time, then I'll start playing around with a manual time step and either increasing or decreasing it according to what's happening in the simulation. And the last thing I want to show you for a time-dependent analysis is the Savings tab. This is a part of the Flow program that not very many people realize, but there's this really great option here called Selected Parameter Transient Explorer. You have to check this checkbox to turn this on, and you have to do it before you run the analysis. And then what you can do is you can click this little 3-dot button over here, and you can check which parameter you want to track for the whole analysis. So basically, I'm saying these parameters, I want to track every iteration for these parameters. All other parameters that I don't check for this Transient Explorer are only going to be saved every 100 iterations. So if there's specific parameters that you want to track in a time-dependent analysis while ignoring other parameters, you do that here with the Transient Explorer. So I'm going to press OK. All right, so now that I've shown you the setup, let's go ahead and look at these results. I'm going to show these. So I could run this as a to show this over time. The problem is there's something wrong with these cut plots. They keep on crashing my SOLIDWORKS when I run them as a time-dependent analysis. But I'll show you this surface plot instead. I'll just show you these as kind of static for now. Basically, you can see here the time is at 40 seconds. So this is the mixing after 40 seconds. Now let me show you this surface plot. And I'm going to hide this mixer so you can see just the surface plot. And I'm going to show this to you rotating. So if I go ahead and right-click results, turn on Transient Explorer, and this little play button pops up, I can hit play, and you can actually see the rotation. All right. And you can do the same with the cut plots, but again, for some reason that I wasn't able to figure out in time for this webinar, unfortunately, those cut plots kept crashing my SOLIDWORKS, so I don't want to do that to you. I will show in the next example, I'll show you cut plots, the Transient Explorer for the cut plots. Okay, the last thing I want to show you here is the flow trajectories. So I'm going to go ahead and unhide that. Show you the flow trajectories. If I animate this, so this shows you the flow trajectories. This is not, the flow trajectories isn't shown with the Transient Explorer. It's not an option for Transient Explorer. So this is only the flow, what the flow looks like at 40 seconds, not what the flow looks like through the whole time frame. But you can see it's absolutely doing that mixing job for us. And the static mixer, if you remember, there was cold water on the bottom and hot water on the top, and in the middle they were mixing pretty well. But with the powered mixer, you see that it is mixing it all throughout the tube. This tube is the same length, same diameter. The only difference between the two is this is powered and the other was static. So you have to decide as the engineer, do I want the slightly better mixing with powered, but I do have to put that power into the system, or am I okay with a static mixer which doesn't require any additional power besides the water moving over it? So I'm going to hide this. All right. So now I want to go back to the static mixer. And, oops, why isn't it static mixer? Sorry. I don't know. Oh, there we go. Okay. So I showed you steady state previously. Now I'm going to show you transient. So I set it up the exact same way as the powered mixer. I put it on for 40 seconds, as you can see right here. Everything is the same setup as the powered mixer, except there's no rotation. It's just static. You can see there's no rotating body in this one. So I want to show these cut plots. On this one, I should be able to show you the transient analysis on this without crashing my SOLIDWORKS. It was working previously, at least. There we go. So that gives you a nice view of what you can see with a Transient Explorer as you track specific parameters in a cut plot. And if I want to see one of the other parameters that I checked on, like let's say velocity, then I can just switch that real quickly to that velocity plot and show that velocity plot as well. Velocity is not as exciting as temperature, so I'm going to put it back to temperature. That's a great feature with Flow Simulation, is this Transient Explorer. And then once again, I can show you the flow trajectories plot that we've been looking at. There's no questions so far. Feel free to ask questions if you'd like. I'm going to hit play. And pretty much the same as before. So around 40 seconds, it reaches steady state. It's not mixing as well as the steady state, so it hasn't quite reached steady state yet. It definitely could go for a couple more seconds. But I wanted to show you the powered mixer reached steady state at 40 seconds. So I wanted to run this static mixer up to 40 seconds to show you the difference. So the static mixer hasn't quite reached steady state in the 40-second time frame, but the powered mixer does. And then you can also look at goals. So I'm going to look at the goals for the 3 temperature goals that I set up previously. So I can see these goals, and I can also see them all on the same plot as a compare and contrast. So the blue line is the hot water intake. The green line is the outlet, and this red line is the cold water intake. So you can see with the hot water coming in the beginning, there's a bit of turbulence with the cold water intake, and then it reaches steady state pretty quickly after about 10 seconds. Hot water is steady state pretty much continuously through the whole analysis. The outlet, on the other hand, ramps up a little bit with the mixing, and then it's almost about steady state here at 40 seconds, as I showed you. So that's how you get to these history plots in the goals. I'm going to pop back into my PowerPoint to give you a quick compare and contrast of these 3 mixers. So this one on the left is the steady state. This one in the middle is the 40-second steady state version. And this one on the right is the 40-second powered mixing version. So you can see the 40-second steady state hasn't quite reached steady state in the 40 seconds in the static mixer. And then the powered mixer does reach steady state in the 40 seconds. And the mixing is just slightly better than the inline steady state mixture. So the powered version does give you slightly better mixing, but again, you have to decide, is the power I input into the system worth that slightly better mixing? Okay. So those are the inline mixers. Second to last thing I want to show you, there's one other thing I want to show you after this, is rotation using what's called free surface. So if I come to my general settings, this is the wizard. Gravity, same thing, gravity coming down. Rotation, same thing. I turn on rotation and it has to be set to sliding. I also turn on what's called free surface here, this checkbox. And when free surface and sliding rotation as well are turned on, you also have to turn on time dependent. So this forces you to be in a non-steady state environment. It forces you to be time dependent. Oh, Alexander, you want me to show you the mesh? Yes, sorry about that. I'll show you the mesh here, and then I'll go back and show you the mesh for the other versions. Fluids. So with free surface turned on, you can have air and water in the same environment, basically. It allows for what's called immiscible fluid mixing. Basically, if you don't have free surface turned on, you can't have air and water in the same environment. They have to be in separate environments, or other immiscible fluids for that matter. You can have air and argon in the same environment, but not air and water and vice versa. And then initial conditions, when you turn on freeze surface, you have to make sure to set the initial fluid as whichever one you want it to be. In this case, I wanted it to be set to air. So that basically says everything in this environment is air. Okay, so at first everything is air, but then you need to say where the water is. And you do that by creating a separate body. And after I go through this setup, I'll show you the mesh on this. Okay, so the separate body in this particular setup, it's in this tank part. I'm going to open up this tank part. And basically what I did here, I'll show you these features. So I created a boss extrude, but as you know, extrusions are straight. So I have these baffles that are kind of poking in, and the extrusion is taking up the same space as the baffles, which wouldn't happen in real life if I filled this up with water, obviously. So then a cool trick that I like to use to kind of form solids to liquid geometry is I use this indent feature. So I can click on the body that I want to cut away as the target body in the indent feature. I can click on the body that I want to do the cutting, and then you just check this cut, and it will literally cut away everywhere that the two bodies are taking up the same space. So using this indent feature, I was able to form this water body like it would, you know, take up this space in real life, as if I poured water in here. Okay, and that created this water body right here. And then what I did in the simulation, after you create the water body, what you do is you come to Flow Simulation and you create a new initial condition. So I created this initial condition. And then you click on the water body. Oh, dang it. Sorry. This is crashing. Sorry about that, everyone. That's the first time that happened for this example. Let me pull it back up here. Okay, so back to initial conditions. In the selection box, I expanded out the tank, I expanded out the solid bodies, and I clicked on the water body right here. And then that then, if you check this box, disable solid components, it then treats that solid extrusion as a liquid body. So basically Flow, you're telling Flow, ignore this solid, treat it as a liquid. And then what you can do is you come down here to substance concentrations and you can switch it to the other liquid that you want it to be. In this case, it's water. Air, I put in the wizard in the general conditions. So I'm setting this to water. You can set the temperature and pressure here. You can give it a velocity in specific direction as well. There's lots of things you can do to this specific water body. What you need to remember is these are initial conditions, so they don't always hold true through the whole analysis. It is going to be water through the whole analysis, but it isn't going to just be flat like this. It's going to be moving around. I set up this ideal wall. Ideal wall is a boundary condition where it's basically a perfect wall. It has no roughness. It's just perfectly smooth. I set up this real wall because my rotating body, I already showed you how to do rotating bodies in the previous example. So my rotating body in this example is just around these fan blades, but I also wanted this shaft to rotate as well. So you can do that by creating a real wall boundary condition. So I choose this option, real wall, and then I can give it a temperature, I can give it a heat transfer coefficient or a roughness, and I can also give it a translational velocity or a angular velocity. In this case, it's an angular velocity of 5 rotations per second, so that part is rotating at 5 rotations per second. And then in the rotating body, I'm rotating this part as a dependency. Basically what that means is I can click this dependency button right here and vary the rotation over time. So it doesn't have to be constant. You can vary it over time. Start off at 0, ramp up at 0.4 seconds, it's going at 5, and then for the full 1 second time frame, it's at 5 rotations per second. By clicking on this little button here, I can see that ramp up in a graph. All right. So that's the setup on this, and then I have a few goals on these as well. You asked about the mesh, so let's go ahead and look at the mesh setup here. With free surface, meshing is very important. So you usually want the mesh to be fairly dense in order to properly capture what's going on in the free surface environment. The meshing that I did here, honestly, is not as dense as it should be. If I was doing this in real life, I would make this much denser, but to conserve on time, I did make these mesh densities less fine than they should be. But you can see I have that rotating region set to 2. I have just the rotating part set to level 3 mesh refinement. And let me load up these results so I can show you what that looks like visually. I see that there are some questions. I'm going to answer them at the end of the webinar. Okay. All right, to show this visually, I'm going to insert a cut plot. I'm going to click on mesh. I'm going to turn off contours, just do mesh. And this is what that mesh looks like visually. So you can see there's a denser mesh around my rotating object and a less dense mesh away from that object. That's generally what you should be doing with these rotating type of events, is increase the mesh density around the rotating object, and then you don't usually have to have as dense of a mesh away from that object. That obviously varies according to situation. So you have to take it kind of situation by situation basis, but generally that's what's going to be happening with the mesh here. So let me show you these two cut plots. These cut plots are immiscible cut plots. So I'm going to edit this to kind of show that to you. Immiscible water. Basically, that just means just show me the water portion of this. And then I'm going to turn on Transient Explorer. Remember, this is only for a second time frame because free surface and rotating region together is very computationally intensive. So I couldn't do 40 seconds like I did in the previous examples. It's just 1.382 seconds, as you can see. You can see the water is moving around due to the rotations, kind of undulating up and down due to this rotating. Remember, it's five rotations per second. So this rotates a little over 5 times in this time frame. See that water undulating there. I'm going to hide those and show you a pressure plot of just the rotating body. I'm going to I'm going to hide that to kind of just so you can see the plot itself, and you can see a pressure plot of just that rotating body using surface plots. All right, I'll hide that. And I turned on ISO surfaces here. I'm going to show this to you. Oh, no, oops. I forgot to turn off Transit Explorer. It's best to do that without Transit Explorer. So I'll show that. So ISO surfaces, this is only showing what's happening at 1.382 as an ISO surface. So it can show you what's happening basically on the top, and a little bit, it's basically showing what's happening in areas of height change, which is right around the rotating region and then at the top. ISO surfaces are very resource intensive. So technically you can show this undulating as a Transit Explorer, but it's so resource intensive that it takes forever to load those results. So usually if I want to see ISO surface results, I can turn on different time points. So I can turn on, get 5 seconds. See, it's not undulating as much. So it's not like a nice animation, but you can see the ISO surface at different time points. And you can also animate it as well. You just have to remember that it's going to take a long time to animate and it's very slow. So that's kind of my experience with ISO surfaces. But I did want to show it to you as an option here. All right. And then there's one other thing I want to show you, and then I'm going to answer these questions. And I'll also show you the mesh in the previous examples. The last thing I want to show you is back in this static mixer. I want to show you there's one other option to do rotation in flow simulation, and that's a very simplified option. So the rotating region is very complex. This next option is very, very simple. And that's basically, you can turn on a new boundary condition just for fans. So I inserted a fan. Basically, I got rid of that static mixer. I just put a solid geometry in here representing the fan. And this isn't water. This is air. Okay. And then the only difference is I got rid of that static mixer, and I also inserted this fan where, as an internal fan, I can say this is the face that the fluid exits the fan. This is the face that the fluid enters the fan. And then I just picked a fan here to show you this. There's lots of different fans that you can choose from in the default database. And if the fan that you choose isn't what you want, you can create fans in Flow Simulation. You can create you can create materials, you can create printed circuit boards, any of these things. You can create your own custom version. So it's very, very customizable. But with fans, you want to make sure you have a fan curve to put in here. If you're creating a new fan to use in Flow Simulation, you want to make sure you put in this fan curve. And you get these fan curves through experimentation. So this is the pressure difference in volume flow rate. So with this fan boundary condition in place, I don't need a rotating region anymore. This is representing that rotating region. It's a much, much simpler way of representing rotation in Flow Simulation. I'm just going to show you the flow trajectories on this real quickly, just so you can see this. So you can see before the air reaches the fan, it's kind of laminar and straight. Not exactly because of this of the 100 degrees Celsius air coming in here. But then after the fan, you can see there's this really nice rotation happening due to that fan. So I just wanted to show you that real quickly as another way to do rotation in Flow Simulation. All right. So now I'm going to go through and answer these questions that were put up in the chat. Feel free to put up other questions. We're already at past the half an hour, but we're going to go a little bit farther and I'll answer these questions. And if there are more questions, feel free to put those up as well. So I was asked by Timo about the goals. So basically, goals in flow simulation are sensors. I can come here to goals. I can insert a global goal. That's for the whole analysis. Point goal, that's for a specific vertice. Surface goal, which is what I put in here on a surface. So I'm basically tracking what's happening on that surface. And then volume goal, that's for a whole part file. And equation goal, basically, I can see what's happening. Let me put an equation goal real quickly here just so you can see that. So let's say I wanted to see the difference between what's coming out minus what's coming in on the room temperature one. I can put in that goal. Usually these goals are variables that aren't specified already in flow simulation. So pressure drop is one that I use a lot to create goals, equation goal for things like that. And then there's all these different variables you can choose from. If I press OK, now I have an equation goal here. And usually I like to rename these. I'll just rename it temperature. But if it was a pressure drop, I would probably rename it pressure drop or whatever. So you can create these equation goals as well. But that's what a goal is it's basically a sensor. So anything that you want to track, you should set up as a goal before you run the analysis. And if you're doing this as a steady state analysis, which is what this is, it also uses these goals to track when to stop the analysis. So when these goals reach steady state, it'll say, okay, these have reached steady state. I'm going to stop the analysis now. And I do that in the calculation control options. Whoops, that's not calculation control options. I do that right here, goals convergence. So some variables reach steady state faster than other variables. You want to make sure that the variables that you care about are in the goals because they're the ones that are going to be reach steady state before the analysis ends. If you don't set it up as a goal, it may not have reached steady state before the analysis ends. So goals are very important in every flow simulation. And then I was also asked about mesh with this. So let me show you the mesh on this one. So I set this up as a level 5 mesh because it's pretty simple, just basically a simple tube. So I was able to go a little bit denser on this one. And let me show you a picture of that mesh. Oh, whoops, wrong cut plane, but I could show you this cut plane too. So there's that cut plane. I'm going to clone this. I'm going to edit it. And instead of the front plane, I'm going to choose the right plane. This is what the mesh density looks like from the right plane. So you can see there's a lot more mesh density around the static mixer than everywhere else, which is what we want because that's where there's going to be all that mixing happening. So we want to make sure we properly capture that mixing with the mesh. And then I'm going to show you the powered mixer next. Let me show you the mesh on the powered mixer. Just to if you unload results, just a little tip, if you unload results in things that you're not using anymore, then it's less likely to crash on you. And that's something that I forgot to do when we saw that crash previously. So I just unloaded those results to hopefully reduce the crashing. All right, so let me insert a mesh here. This is a level 5 mesh as well. So you can see on this powered mixer, because the geometry is closer together, that level 5 mesh does mesh this little bit denser than the static mixer. So if I was doing this in real life, I would probably have put a lot more effort into meshing this properly and make sure the two meshes are a lot closer together. But I just wanted to show you, the main purpose of this webinar is to show you the rotating region and free surface and rotating region together. Okay, last question I have up here is, he asks, so if you have a low mesh resolution, have you tried thickening the mesh and comparing simulation results? Honestly, in these particular examples, I did not do that. That's called mesh convergence analysis. In mesh convergence analysis, what you're doing is you're doing several simulations. You need at least 3 to compare properly. Sometimes I even go up to 5 or 7 simulations. And the only thing I'm changing between the different simulations is the mesh density. So I will increase the mesh density in each new simulation. You create a new simulation by doing this. You come up here to the projects, you right click, you click on clone. And then I usually, if I'm doing an increased mesh density, I'll usually put M2, and then I'll increase the mesh density for this one, run it. And then I'll clone this one and I'll make an M3, increase the mesh density here, run it. And basically what I'm looking for is I'm looking at my goals, the variables of interest, and I want to make sure if they're jumping around or not. If they're jumping around as I'm increasing the mesh density, then I want to continue increasing the mesh density until they stop jumping around like that. And once they've leveled out between 2 different simulations, that's when you know, okay, this is the mesh density that is giving me proper answers, and you can just use that mesh density moving forward after that. Hope that makes sense. Do we have any other questions? It doesn't look like it. We're about 10 minutes over when we said the webinar would end. So if there are no more questions, then we'll end this webinar. And it's been great talking to you all. I hope this has been helpful. If you'd like to learn more about flow simulation, please feel free to reach out to us at GoEngineer, whether you want to purchase flow simulation or if you already have it and you just need help setting up a simulation from scratch. That's basically what I do all day long. People put up their problems for their simulations in front of me, and I either help them set it up from scratch or I help them get through an issue that they're having with a simulation setup that they've already put together themselves. So please feel free to reach out to us at GoEngineer. You can just come to our website, GoEngineer.com, and believe you can come to our technical support, and I believe we have a number here for technical support issues, and then an email as well if you want to email. All right. Okay, no problem, everyone. Thanks for attending. We'll talk to you all later.